So Coulomb's law is the basic law of electrostatics. We can use it to calculate the force that, say, a positive charge exerts on a nearby negative charge. But that leaves us with an unanswered question. How does one charge know that another charge is there? Coulomb's law tells us how to calculate the magnitude and direction of the force, but it doesn't tell us how the force is transmitted through empty space from one charge to the other. To answer this question, we need to introduce the field model, which was first suggested in the early 19th century by Michael Faraday, a British investigator of electricity and magnetism. So what do we mean by field? What this term field means is that there's just an alteration of space around whatever it is we're talking about. And we can talk about three types of fields. Okay, we can talk about a gravitational field. We can talk about magnetic fields, or we can talk about electric fields. Now, a lot of the things that we've done already have been around these gravitational fields, okay? All motion and forces and all of these things are happening within Earth's gravitational field. All a gravitational field is just an alteration of space around some type of mass, okay? An electric field is the alteration of space around a charge. A magnetic field is the alteration of space around a magnet. In the field model, it's this alteration of space around an object that is the agent that exerts a force on another object. So with a gravitational field, the alteration of space around a mass is what exerts a force on other masses brought into that field. So the same is true for an electric field. When a charge enters the electric field of another charge, it's that field that exerts that force on that object. Now, where there's a difference between a gravitational field and an electric field is that the Earth's gravitational field, when we take an object and put it in the Earth's gravitational field, the field around that object does not exert a measurable force on the Earth. With charges, that's not true. If you have a group of them, the forces that they exert on each other are significant. We can't ignore them. It'd be like having 3 or 4 planets scattered around in a volume 1,000 times smaller than the solar system. They'd all exert extremely large forces on one another. So because of this, we have to treat electric forces between charges different than how we treat gravitational forces between masses. So we're going to begin by our investigation of electric fields by looking at what we're calling a field model that describes how two charges interact. The first part of this field model will be that source charges create an electric field. So this is some charge that sets up a field, and then we're going to investigate that field. And a separate second charge in that field will then experience a force exerted by that field. So we're going to look at this as though, say it were a planet, we bring an object into the gravitational field of the Earth, same kind of thing. We'll have a field that is set up by a charge, and we'll look at other objects brought into that field. So the electric field is a way of describing how a point charge or several charges influence the space around them. The electric field at various points around some charge distribution can be analyzed by measuring the force of the distribution creates on a test charge. So we can put a test charge within an electric field and then see how that field then behaves. The electric field is a vector quantity. We abbreviate it E, it's electric field. It is a vector. And the direction of an electric field is always based on the direction that a positive test charge would be forced. So it's the direction of an electric field is the direction that a force on a positive test charge would point. For example, say we have some charge here. This is a positive charge. This is our source charge here. And then we place a test charge, a positive test charge within that field somewhere, and it's at this point right here, this thing is going to experience a force off in this direction. Okay? If we move it over here, then it experiences a force off in this direction. We move the thing closer, it experiences a force greater. We move it further away, it experiences a force that is reduced of that. So then, kind of our main point here is that the electric field points in the direction that a force on a positive test charge would point at a given location. So that's direction of electric field. So let's take a look at magnitude of electric field. Our expression for electric field is this E equals F over Q. So this is the electric field at a point as defined by the force on the charge Q, It's important to note here that this charge Q in this equation is that the Q here is not the charge that sets up the field. The Q is the test charge that we place in the field. So this is it's like F equals ma. The m is the mass of the object in the gravitational field. It's not the mass that sets up the field. So this is the same kind of thing. The Q is the charge we put into the field, not the charge that sets up the field. So the basic idea, just to kind of give a little summary before we go into working some problems, is that the basic idea of the field model is that the field is the agent that exerts an electric force on a charge. So let's make note here of three important things about the field. First, the electric field is a vector that exists at every point in space. The electric field diagrams that we're going to see later will show a sample of the vectors, but there is an electric field vector at every point, whether one is shown or not. Second, the probe charge, the test charge, is positive. The electric field vector points in the same direction as the force on this positive test charge. And third, because Q appears in this equation above here, it might seem like the electric field depends on the size of the test charge. It doesn't. We know from Colins Law that the force on Q is proportional to Q, to the charge in the field. Therefore, the electric field is independent of the charge Q. The electric field depends only on the source charges that create the field. To make more sense of this, think about a gravitational field. When we put an object into Earth's gravitational field, does it affect Earth's gravitational field? No, it doesn't. The same is true for an electric field. What that means is if we put something in Earth's gravitational field, it's not going to alter that field. Okay? The same is true of charges. When we put a charge into another electric field, it's not going to alter the electric field of that original charge. So that's a couple of things there, for three things, main points that you should make note of. So then, on to some problems. So example A. An electric field has a field intensity of 2 times 10 to the 4 newtons per coulomb. If the force acting on a test charge is 6.2 newtons, what is the magnitude of the test charge? So we start out with E equals F over Q. This electric field has a field intensity, or sometimes we call it a field strength, of 2 times 10 to the 4 newtons per coulomb. I'm not sure if I mentioned that before, but the units of electric field are the newton per coulomb. The force on the test charge is 6.2 newtons, and we want to know the size of that test charge. and it ends up 3.1 times 10 to the negative 4 coulombs. So then for example B, we have here an electron traveling at 2.3 times 10 to the 5 meters per second with a direction as shown in this diagram. Okay. This electric field, so these lines represent the electric field in the direction in which it points. So this electric field has a strength of 280 newtons per coulomb. And we're asked to do four things. We're asked to analyze the electric lines of force and figure out what direction is the force acting on that particle. What is the magnitude of that force? So how big is that force? What is the acceleration acting on the electron? If the electron travels a distance of 3 millimeters into the field, what is the distance it will be deflected on from its original path? Okay, great. So let's first look at part A. Analyze the electric lines of force. What is the direction of the force acting on the particle? So let's look at this. This particle is an electron. Okay? The electric lines of force, the electric field, so the lines representing the electric field point in the direction that a positive charge would go when in that electric field. Well, we have a negative charge. So what that means is our electron will experience a force opposite that of a proton. A proton, if this were a proton going into this field, it would go in the direction of the electric field. The force on it would point in the direction of the electric field. Because this is an electron, it points in the direction opposite the electric field. So because this is an electron, the force on it will be down. So as it enters into this electric field, it's going to go and be forced in this direction here. Okay, so number B then asks us to figure out what the magnitude of the force is on this thing. So what we're going to do, when we have an electric field, we have a known electric field, we want to know the force on a test charge. We're told that this electric field has a magnitude of 280 newtons per coulomb. We want to figure out what the force is on this proton. Oh, great. Okay, so where do we get Q, right? So take a minute, pause the video, go get your equation in table of information, and there you will find the charge on a proton. And what you should see is that the charge on a proton is 1.6 times 10 to the negative 19 coulombs. Now also look at the charge on an electron. You're going to see that the charge on an electron is also 1.6 times 10 to the negative 19, but it is negative. And we go through this and we find that the force on this electron is this 4.5 times 10 to the negative 17 newtons. Okay, great. So part C then. Part C wants us to find the magnitude of the acceleration on this thing. So what are we going to do? How are we going to approach trying to find the acceleration on this electron? So let's think about it. This electron is in this electric field. It's experiencing a force. What do we know? And we know by looking at also at our table of information that there is a mass for electrons. So what do we know about the force on a mass in relation to acceleration? Well, we know that force is equal to mass times acceleration, Newton second. So when this thing enters this field, I mean, it may also be in a gravitational field at the same time, but the thing is, a gravitational field would have such little minuscule effect on the acceleration of this electron that we can essentially ignore any effects from any gravitational field it may be in, and we can look only at the electric field on the thing. Okay, So it has this 4.5 times 10 to the negative 17 Newton force on it, and we look at that table of information and we see that the mass of an electron is 9.11 times 10 to the negative 31 kilograms, and we want to find the acceleration, and the acceleration is 4.92 times 10 to the 13 meters per second squared. So as long as we know that the only force acting on this thing is this electric force, then we just use a simple F equals ma. Great. So on to part D. So for part D, here's our picture again. On part D, we're told this electron travels a distance of 3 millimeters in the field. And we want to know the distance it will be deflected from its original path. So its original path is going directly into the field this way. And it's going to be deflected because there's a force acting down on the thing. Okay? So as it goes into this field, we can see that it will... I'm going to get a different color. There we go. It's going to go kind of in this pathway here. Okay? And we're told in the problem that it goes into the field 3 millimeters. So this is 3 millimeters distance right here. Okay? And so what we want to know then is how much will it be deflected within that field. Now this may seem really complicated to begin with until we realize that this is not any different than throwing a ball horizontally in a gravitational field. This is just like asking what the height of a table is when we have launched a ball horizontally off of it. All the same things are true. The horizontal velocity is constant. The acceleration is all vertical. All we have to do is find the time that it takes to drop this distance, and I say drop with like quotes around it. And then we would find that delta y distance right here. Okay, so this is really, it's just kinematics is all this is. So all we're going to do is start out by looking for the time that it falls by using the second kinematics equation. We're going to find the time by using the constant velocity equation. Okay, because we know the x distance, which is the 3 millimeters. We know the horizontal velocity, which is the 2.3 times 10 to the 5 meters per second. We can easily figure out how much time this takes. So it's going to look like this. And we're going to end up with a time of 1.3 times 10 to the negative 8, which is a very short amount of time, even for an electron. And of course, because we remember what it's like to do some kinematics, some horizontal launch things, we know that the next thing that we're going to do is simply use the second kinematics equation to figure out that distance that it drops. So, we'll start out yf equals yi plus vyit plus 1/2 at squared. Well, because we can say then that we start out, our initial position is at a 0, and our initial y velocity is 0 because it's all x velocity as it enters this field, we can just change this to yf equals 1/2 at squared. So we just plug in our values. We get our acceleration from part C. We get our time from the previous part there. And we end up with a distance of 0.0041 meters, which really we could also report as 4.1 millimeters. So that's kind of the electric field beginnings here. The only little thing left to kind of deal with on this part is electric field lines, and that's just a way of representing what an electric field looks like. So say we have a positive charge. We draw lines in the direction that a positive test charge would, the force on a positive test charge would point if it were placed in that electric field around this thing. And so a positive charge looks like this. If we have a negative charge, how do you think that a positive test charge would point? The force on a positive test charge would point, of course, toward that force. Or sorry, toward that charge. So this right here is the electric field around a positive charge. This is the electric field around a single negative charge. So what happens if we have, say, two charges, both positive, like this? Well, they're going to affect one another, and the electric field between them is going to look something like this. They're going to be repelling one another. So this is how two positive charges would, the electric field around two positive charges would look. Here's two negative charges, of course, with the electric field being shown pointing toward the negative charge. And here is a positive and a negative charge with the electric field pointing away from the positive charge toward the negative charge. So all three of them together looking like this right here. We got the positive charges, positive charges here, negative charge here, positive and negative here. So try to imagine what, say, multiple charges would look like, right? So if we had, say a positive charge, negative charge, and say another positive charge right here, what would the electric field look like around that?